Speaker is Patrick Fraser, who's coming to us from the University of Toronto, and he'll be speaking to us about knowledge, how, and the semantics of physical theories.
Great, yeah, thank you very much, and thanks a lot for the opportunity to present this work here. This is very much still sort of an early stage project, so if you have comments or suggestions or early stage interventions, please feel free to share those with me. That would be much appreciated. But basically what I'm undertaking here is kind of a reevaluation of a certain kind of received view about the way that we the way that we evaluate the truth conditions of physical theories. So here are two questions that one might reasonably ask. First, what are the truth conditions for physics? Under what conditions are the assertions made by physical theories true? Second question we might want to ask, can we know if these truth conditions actually obtain? And we might think that it's desirable to be able to answer one in such a way that we can answer two positively. So we might want to be able to say, you know, physics has truth conditions. Those truth conditions somehow tell us what the world is like in some substantive way. And moreover, it's actually possible for us to know when certain claims made are true or false. If you can answer these questions in this way, you might see an inroad to a kind of defensible position of scientific realism that you might find highly desirable. I should qualify this by saying, presently I'm not really making any sort of stipulations about what relevant theory of truth is being presumed, but I take it that this is a desirable situation for us to find ourselves in. Now it happens that there is a received view for the sort of truth conditional semantics of physical theories. It's very much motivated by the kind of Tarskian truth in a model conception of truth conditions. So you pick your favorite physical theory, T. T asserts various sentences expressing various structural relations between physical quantities. Then there are particular sorts of mathematical structures in which these sentences are interpreted. And the structures which satisfy all of the T sentences are then called the models of the theory T. These are like exact models. And T is true of a particular target system S, just in case there exists some T model which is isomorphic to S in all appropriate respects. This is a kind of received view. If you're familiar with the syntactic semantic debate about theories, you'll see that this is actually agreed upon, like both sides agree about this. They disagree about whether the syntactic structure of the theory underwrites the set of models or if the models are what give rise to the appropriate set of axioms. But nevertheless, within that debate, this is kind of the received view about how the truth conditions for physics are supposed to work. So as an example, you could imagine as your theory, you've got Hamiltonian mechanics. You can pick some sort of model where you specify a Hamiltonian and a trajectory through phase space, and then there's some target system like a real block that actually has mass affixed to a real spring that is in some sense appropriately isomorphic to the model that you've written down. Now, the project that I'm undertaking here is to basically give a battery of objections to this and try and modify it in an appropriate way that we can still use it for stuff. So the first problem, that's a fairly familiar one in the philosophy of science, is that this isomorphic in all appropriate respects clause is widely underspecified. There's of course lots of different ways various structures can be isomorphic to one another. They can be topologically isomorphic, they can be measure theoretically isomorphic, there's various kinds of isomorphisms that can exist. And there's no obvious sort of single shot solution for how to make sense of this claim that works in all cases. There's sort of a lot of different discussions about how to solve this sort of problem, and they all kind of have a familiar flavor, which is that the relevant notion of isomorphism in a given case is somehow supposed to be determined by the purposes for which the representation is going to be used. So when we are thinking about whether or not a theory is true of a system, and we're asking whether or not one of its models is isomorphic to that system, what kinds of inferences we might want to draw about the system are going to determine what the relevant standard of isomorphism are, something like that. Lots of people have explored different versions of this kind of view, and I'm not going to say very much more about it. But this is one kind of problem that the received view encounters, and this is one way that we can try and start to fill it in. Here's a second problem that some people will find very compelling, some people will find less compelling, but I think it's worth considering it. And this is that the received view commits a kind of a type error. So you might think target systems are concrete, while the models of our theories are abstract. Isomorphisms tend to be maps from one mathematical object to another mathematical object, and in that respect, they seem to be things that can only relate abstract entities to other abstract entities, and so they can't relate target systems to models. The idea here is that it's wrong to suggest that abstract models can stand in any sort of relation of objective similarity codified by an isomorphism to a concrete target system. just the wrong kind of thing to use to describe the relations between things in the world and the ways that we represent them. Whether or not you find this kind of problem compelling or not, there is a way that we can sort of fill it in, at least locally for our purposes here. It's motivated by a sort of taxonomy that von Frosten gives us for different kinds of models. So von Frosten describes 3 different kinds of models that are relevant for scientific practice. The first are data models, and these are the models that are composed basically of finite collections of observed statistics from real experiments. You go into your lab, you pick up a bunch of stuff, you measure it, you write down what you see, you put all the stuff that you saw in a list, and that list, uninterpreted, is your data model. That's the thing that makes really direct contact with the stuff in the world. Then we have surface models, and surface models are what we get when we kind of minimally interpret these data models. By minimally interpret, I mean something like we take these chunky statistics and we turn them into smooth probability distributions. We might take the labels on our detectors and identify them with values of particular quantities that appear in our theory, something like that. And when we do this, when we build this surface model, we're left with a mathematical object that is at least of the appropriate kind to be compared to theoretical models. And then we also have the theoretical models themselves. And these are those mathematical structures which satisfy a particular theory. And so the solution to this problem is that the relevant notion of isomorphism that's supposed to be entering into our truth conditions is really a relation between theoretical models and surface models. So we can kind of detach the problem by saying there's the target systems in the world. When we poke and prod them, we get our data models. Then there's this hard problem of figuring out how to find the right surface model to associate with that data model. But once we've gotten there, then we don't run into this type error. Then suddenly our isomorphism is really between 2 things that are, at least in principle, relatable by an isomorphism. Okay. So at this stage, if we identify these 2 problems and we fill them in the way that I suggest, we get something that resembles an intelligible truth conditional theory of physics. Sort of a coherent way of saying what it would be for a physical theory to be true of a particular target system. But now we want to ask whether or not it's possible for us to know whether or not these truth conditions have ever been satisfied. And this is where we encounter what I think is a much more interesting problem that Eric Curiel proposes in a very interesting recent paper. So the problem Curiel identifies is as follows. It's sort of a historical fact that very few exact models of our physical theories are actually known to exist. So we can do axiomatic quantum field theory and we can build a handful of constructive quantum field theories, but we don't have any interacting, we have very few of those. There's not a lot of exact models on offer. Likewise, in general relativity, we have a handful of exact solutions to the Einstein field equations, but we don't have copious collections of models at hand. Moreover, in cases where we do have exact models for our physical theories, and by exact models I mean here things that perfectly do in all respects globally satisfy the axioms of our theories, if we want to put it that way, the exact models that we do have at hand for our mature physical theories are things that we actually already know to be inadequate for representing the kind of realistic target systems that we encounter in the world. So we have a few constructive quantum field theories at hand, but none of them look like quantum electrodynamics, for instance. We have some exact solutions to the Einstein field equations, but the ones that we use when we're doing cosmology, for example, tend to be highly approximative. We frequently look at things like linearized gravity and so forth. So if the received view is right, if the received view of the truth conditions for physics is correct, then we actually don't know if the truth conditions for any of our best physical theories obtain. And the reason we don't know this is because we don't know of any exact models that exist that stand in the appropriate kinds of isomorphic relations to surface models of realistic target systems. So what we have here is an obstruction to our epistemic access to the truth grounds of our physical theories. And this obstruction comes out basically because of the way we've set up this semantics for our theories. I should note that this is actually a problem for realists and for anti-realists. So if you think that when I talk about the truth conditions of a theory, I'm saying something about the stuff in the world having the properties that we attribute to it by our theories in some thick sense, you might be a realist and you have this problem. But it's also a problem if the sorts of claims you're trying to evaluate as true or false are claims about the empirical adequacy of your physical theories. What we have here is, if we just kind of naively fill in this truth conditional account of the semantics of physics, we're unable to explain the possibility of our knowing that any of these truth conditions actually obtain. And this seems like a big problem. So Curiel proposes what I think is a very compelling solution to this problem, and it's not actually that surprising, which is that we should just include the inexact models of our physical theories among the meaning structures that are supposed to underwrite their truth conditions. So in practice, these sorts of inexact models, things that are approximate, perturbative, linearized, and so forth, when these are used correctly, these are clearly the sorts of things that are already responsible for our existing epistemic commitments to our physical theories. The sorts of reasons why we believe in the standard model of particle physics are not reasons given to us, at least automatically, by something like axiomatic quantum field theory. They're given to us by these approximate theories, these theories that are inexact. So this sort of tracks scientific practice fairly well, but it requires supplementing this semantics with an account of the pragmatics of inexact model use. So inexact models are generally very badly behaved in certain places, and they tend to break down outside of certain regimes. And so for an isomorphism between a model, like a theoretical model, say an inexact one, and a surface model of a target system, to actually establish that that theory is true of that target system, it's required that the system be within a kind of regime of propriety of the theory. And Curiel goes through a characterization of what we might think these regimes of propriety look like and how we come to figure out what they are. Moreover, to determine when a theoretical model can be used, and also in order to be able to generate surface models for realistic data models, we actually need to be able to represent our first-person experimental access to the systems that we're studying. So in order for us to be able to extrapolate something looking like a surface model from a collection of observations, we need to know the nature of how we were able to get these observations out of the system. We need to be able to represent where the observer was. So we have to be able to schematize the observer in Curiel's language. So this there's obviously a lot of steps to be filled in here with respect to what this pragmatics is supposed to look like, but the idea is that once you are able to fill this in, you can supplement this semantic theory for physics with an appropriate pragmatics that makes it look a lot more viable. So here's the kind of semantic theory that we end up with. A physical theory T is true of a target system S in a particular inferential context when there exists a data model of S, which, when our experimental access to S is appropriately schematized, generates a particular surface model of S. And the surface model of S is isomorphic to some exact or inexact theoretical model of the theory in question in the relevant sense determined by the inferential context. And S lies in the regime of propriety of the model at hand. So here's a semantic theory that you can put on the table. This is a truth conditional theory for physical theories. And what we see is that when Curiel introduces inexact models into the sort of meaning structures that underwrite the semantics of physics, this allows him to avoid the obstruction that he identifies. This allows him to get around the sort of peculiar impossibility of explaining how we can possibly know that our theories are true. But it doesn't ensure that that kind of epistemic access is guaranteed. It doesn't ensure that that kind of epistemic access is generically possible. In particular, it's totally conceivable that other obstructions could arise. So here's an example of another kind of obstruction that could arise. So suppose that we've established that there's some theoretical model, and that's isomorphic to a particular surface model of some target system, and the target system in question is within the regime of propriety of the theory. So we've established everything that on the theory just put forward we would need to establish in order to say that that theory is true of the target system. Well, to actually infer that the theory is true of any particular target system that you could find in a lab and point to, the data model that was used to generate the surface model in question has to be in some sense representative of that target system. So an important fact is that data models are typically not generated by observing a single system. They're usually generated by observing large ensembles of systems. So except for in some contexts like experimental cosmology, generally when you try to build up a data model, when you try to do actual experiments to get aggregate statistics that are supposed to inform you about the behavior of a system, you don't look at one system, you look at many copies of the system. You build a large ensemble of systems and you carry out repeated measurements on each element of the ensemble. But in order to say that a particular data model is actually in the appropriate sense representative of any individual target system in that ensemble, we have to first establish that ensemble is sufficiently uniform for the resulting data model to tell us anything about the components. So, you could imagine picking up some measurement apparatus and just going around the world and pointing it at random objects and taking observations and writing them down. And if you did that, you'd get a huge collection of data, but you wouldn't think that the data in that collection is in any respect representative of any of the individual elements of that ensemble. So if you just go around randomly measuring a bunch of arbitrary objects, you don't think that the resulting statistics are going to tell you anything about any particular member of that ensemble. So in order for us to sort of get this story off the ground in the first place, we have to know that the ensemble that we're using to generate a data model is in an appropriate sense uniform. More specifically, we have to establish that experiments prepare systems with broadly the same causal profiles when we're building up a data model. What do I mean by this? I mean that we need to be able to establish that when we create the ensemble of systems that we're using to generate our data model, that the elements of that ensemble are such that they behave in broadly indistinguishable ways, indistinguishable with respect to the kind of experimental apparatus that we have at hand. Now, in realistic experimental settings, I claim, this is actually reasonably easy to establish. The reason that this is reasonably easy to establish is because experimental physicists tend to have highly reliable knowledge how. So I'm going to explain more what I mean by this. This is a distinction made famously by Ryle. We can say that an agent has knowledge how to phi if they have the ability to intentionally phi under appropriate circumstances. There's a large existing debate about whether or not knowledge how is a distinctive kind of knowledge from propositional knowledge. I don't want to touch that debate at all. I don't think that that's relevant to this particular issue. But the reason I'm introducing knowledge how is because if any attributions of knowledge how whatsoever are warranted, surely the attributions of knowledge how to experimental physicists are among the best candidates. Experimental physicists have remarkable control over the behavior of systems in their labs under highly controlled conditions. So the claim I want to make is that we're often warranted in attributing to experimenters knowledge how to prepare physical systems with broadly the same causal profiles under highly controlled conditions. This is, I'm not going to independently argue for this claim because I think that Ian Hacking and Nancy Cartwright have done enough work to that effect already. But given that we're already able to make these knowledge how attributions to experimental physicists, we can then say that if experimenters know how to prepare physical systems with broadly the same causal profiles, then the data models produced by their experiments are representative of those physical systems in the relevant sense. That is, the target systems whose preparation is used to generate the data models are a sufficiently uniform ensemble that we can think of that data model as actually telling us something about the elements of the ensemble. But then if a data model is representative of a system, then establishing that the associated surface model is isomorphic to some theoretical model and within its regime of propriety suffices to establish that the theory is true of that system. So what I'm showing here is that if we take seriously the kind of curial version of the semantics of physics, and we appropriately allow ourselves to make knowledge how attributions to experimentalists in a way that seems sort of prima facie highly plausible, then we are actually able to explain how it can be possible for us to know that the truth conditions of our physical theories have obtained. So the picture that I'm putting on the table here, I argue, I'll say more about this in the Q&A if people are interested. I think it's very compatible with particular kinds of realism, but nevertheless, it's a very deeply pragmatist picture of physics. So I think that there's reasons to believe that we can very easily slot in a kind of hacking brand entity realism into this picture, or the kind of realism about laws that Cartwright defends. But to see that this is very much a pragmatist theory, we can see that truth conditions are ultimately relativized to an inferential context. You might actually ultimately think that in trying to give a good truth conditional semantics for physics, I've ended up kind of arriving at truth conditions that are acceptable only given a particular kind of inferential setting. And so ultimately what you're left with is a kind of inferentialist semantics. So that's kind of the result of addressing the first problem that was described. If we look at how we address the second problem that was described, we see that the truth conditions here don't actually utilize any sort of direct correspondence or representation or mirroring relation between models and systems. And if we recall how we addressed Curiel's problem, or how Curiel addressed Curiel's problem, we see that the truth conditions ultimately also have to be relativized to a schematization of a particular first-person observational perspective. So here we see really that we're building in a highly agent-oriented picture of the physical systems when we're trying to give truth conditions. Moreover, the thing that ensures our epistemic access to the truth grounds of our theory ultimately bottom out in our knowledge of the reliable capacities of experimenting agents. So our ability to say that agents have particular agential capacities is what ultimately is responsible for us being able to say that we know that the truth conditions of a theory have been satisfied on this revised picture. So I'll stop it there, and I'll thank you all very much for your attention.
Thanks, Patrick. This is very interesting. I think you're on the right track to something really good. In particular, I think you're absolutely right to emphasize towards the end the know-how of the experimenter. So I think I'm happy with the sort of where you end up, but I'm a little worried about where you start. Because you start asking about the truth conditions of physical theories. And I think we should step back and ask, what is it that we should be asserting is true? Newton's law of gravitation, GR, the standard model of particle physics. What should we be asserting about those? Not that they're true, but they give a very good approximation to the truth in their domains of applications. And this is not a novel insight, that's Newton's fourth rule of reasoning. So I think we should be looking for the truth conditions of the statement that we should actually be asserting. Namely, GR gives a very good approximation to the truth, to whatever what's really going on out there. And so I would take that as a starting point. Look for, well, what are the truth conditions of that? And the reason for that is that, okay, I can take the class of models of GR, and what I'm asserting is that within a certain degree of approximation, what's happening out there in the real world, what's happening out there in the real world is appropriately close to one of those. And notice I can have good reason for that without actually being able to write down in explicit closed form which one it is. I think there's this mystique, this complaint that we don't have exact models, I think is completely and utterly 100% misguided. Because it's an arbitrary distinction. What's it mean to have an exact model, right? Well, we can write down a closed form in terms of some standard functions that happen to be programmed into Mathematica or something like that. Do I have a closed form of the Bessel equation? Yes, because we've defined one of those standard functions as this is the solution of Bessel's equation. Right? And I could take any problem and say, yes, here's a closed form of solution to this. Define blah, blah, blah function as the solution to these equations. Right? So I would recommend just completely disregard concerns, I forget which number concern it was, about not having like exact closed form models of our theories.
Mm. Yeah, I mean, so I think that so I think that's a very helpful suggestion, and when I figure out how to appropriately repackage all of this, I think that that'll be very helpful. But I think that one of the benefits of introducing that distinction is just that it allows you to then talk about the other models that we readily pick up and do use that are not of this nice closed form. And so, like one thing that you can, so it seems like you can make a trade-off between saying, my theory is true of a particular system in the sense that there's an exact model of my theory that is exactly true of that system, or you can say, here's a sophisticated story about the pragmatics of how I'm going to use my models that allows me to make a very localized claim about how a particular sort of model allows me to make true statements about a particular target system. And so, one of the true statements that I can make using an approximation is that the value of some quantity is approximately such and such. And that's a perfectly true claim. It's not untrue that if, for instance, I can only discern values to a certain resolution, medium-sized dry goods at low velocities and not too massive tend to, truly obey Newton's laws insofar as what I mean by true is relativized to the standards of the inferential context that I'm operating in.
Yeah, I agree. So the assertions that you are going to assert as true are always going to have implicit, and it'd be better to make it explicit,
Yeah.
some claim that, some standard approximation.
Mm-hmm. Good, thanks.
First of all, I'm pretty sympathetic to this inexact model. Understanding what's going on. A few comments and a few questions related to what you mean the model itself and more. One comment is that I'm very confused what you mean by model here, specifically. Maybe this is just a small parenthesis, because you use it in different ways along the talk.
Mm-hmm.
At some point you said that Hamiltonian mechanics and a model is a harmonic oscillator. And then the solutions of the equation model as just a model of a model or something like that. But then you said the theory is generativity and a model is a solution of generativity. It's a different thing. And then you said, so in fact, I'm always confused what philosophers do by model, because they keep jumping into different.
So are we.
Even clarifying that, I suppose this can just be cleaned up. And my second comment is, I listened to that, to this argument, and I think that this is the way I was told in my physics department how physics works. I was never told that I never heard models in my physics education. I knew that there were theories, that were a solution of theories, and then the solution of the theory were compared with tables of data with mistakes, and if the tables of data sort of
Close enough.
or more precisely, that certain relations between data are confirmed, what the analogous relation that the theory predicted, then not at all that the theory is a model of what happened in reality, or that it's a mirror of what happened in reality. But the theory tells me something useful about what happened, knowing in every single specific physical situation that what is going on there is far, far more than any theory had it about it. Because just in the simplest situation, your stone on a spring, of course springs are not harmonics, of course there is blah 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 blah, there's friction, etc., etc., etc. So third point, so you see where we're going, this is very much in the same direction way. Third point, so dependent. Third point is when you said what about if I collect randomly data? I have table of data, but they don't correspond to the same system. And you argued, well, but there is a competence in the experimentalists that sort of know what they mean when they bring together I would say that this is part of theoretizing itself. Take a case in which you don't have any competence and you have exactly to do this job. A typical case in astrophysics, for instance. There are many signals, gamma ray bursts. So you have all this gamma ray bursts. You do statistics. You have theories about that, and then you sort of, that's practical science, start to figure out that actually that isn't a phenomenon. These are two phenomena. They're two completely different phenomena. One is, I don't know, neutron star collapsing. Another is a star running around. So you take this bunch of data, you split it in two, and you say, okay, this satisfies that, this satisfies that. So it's a process of figuring out which class of measurement can be, let's say, predicted by which class of theory. It's not an a priori necessary knowledge for getting there. It's part of the competence needed to make up this complicated connection between the equations and measurements.
Yeah, so with respect to that third point, I think that the thing that I think was more or less ignored in the philosophy of science until kind of around the 80s was the fact that experimental scientists, so leaving aside the kinds of experimental sciences that are engaged with sort of like wait and see kind of measurements, where you're sort of waiting to see like what signals come in from somewhere else, but like the kinds of experiments where you're really setting things up and trying to make something happen, experimentalists are really good at creating phenomena. I mean, that's the term that hacking has. But like, they're really, really good at setting things up in sufficiently controlled environments so that when they press a button, the same thing will happen over and over again. And so, yeah, you can end up in situations where you've got a collection of observations, and it's the task of the theorist to try and identify a nice way of partitioning which observations came from which kind of thing and which observations came from which other kind of thing. But in the cases of experimental physics that I'm kind of interested in, we don't have to do that because the experimentalists have already done it for us, in the sense that they've figured out what kinds of stable patterns of phenomena they can generate in the lab. And that's kind of what's playing a big role in this, at least in the picture. So in cases like astrophysics, where there's sort of this wait and see kind of structure to the way we get observations, there's still work to be done. But like the hacking line about like, if you can spray them, then they're real. And by the way, there's a lot of things we can spray really well, I think that has to play an important role in how we attribute meaning to terms in our physical theories, if our physical theories are supposed to be telling us about the sorts of stuff that we're spraying. Does that make sense?
Yes, it does. But particle physics, you just
bash them together.
Yeah, just bash protons, and then you have zillions of things. And the problem is just, this is a muon, and then I do muon physics. This is a jet quark, and then I do quark physics. So it's not. There's a clear distinction between the two cases, I would say.
Maybe we can continue the conversation during the coffee break. Let's thank Patrick so much.
Thanks a lot.